All right, here we go. So this first lesson, or this next lesson here that we have today, we are going to be talking about using parallel lines in our proofs. A lot of these theorems that we're going to see here initially, these are the converses of the theorems that we learned yesterday here. So notice that they all say converse here. These are going to be very similar to the theorems that we learned in the previous lesson here. So you had like the alternate interior angles theorem. If you have parallel lines and alternate interior angles are congruent, you have the same thing for corresponding angles and then alternate exterior angles. Then you also had the one that was dealing with supplementary angles with the same side interior angles theorem, and those would be supplementary. So we can use the converse of each one of those theorems when we want to do the opposite thing. When we start out with congruent angles, then we can go and say then the lines are going to be parallel and so on and so forth there. So let's look here individually at them. So you got, if two lines are cut by transversal, so the alternate interior angles are congruent, then the lines are going to be parallel. So as long as these two angles are congruent, J will be parallel to K. Same thing with the corresponding angles. And remember, these are kind of like the same general position, top right angles for both of those, 6 and 2. So since those are congruent, then we can say the lines that they're touching are parallel. Same thing with alternate exterior angles. The lines are parallel. I guess they left out the blank there. And then the only one that's a little different is the consecutive interior angles. So if we say that these are supplementary, then we know that the lines are going to be parallel themselves. All right. So we're going to get practice writing these out in the proofs. Now, each teacher is a little bit different as far as how they like these written. So I'll try to go kind of what most of them like to see, and then your teacher will let you know if they want to see something different here. But check this out here. So you got A is parallel to B. So they give us that the lines are parallel from the beginning. So this is actually going to use one of the proofs from the previous lesson here. So the next part is just identifying the angles here. You had 1 is congruent to 3. All right. So we know that because we have the parallel lines. So this is going to be that corresponding angles theorem. And here's how most of the teachers like it written out. If you have lines that are parallel, then the corresponding angles, and usually I use like a little angle symbol, are congruent right there. So you want to write it in a conditional statement. If you have lines that are parallel, then the corresponding angles are congruent. So you can use little symbols because that's kind of a lot to write in one little line. But yeah, that's pretty much it there. That's kind of like a one-step proof there of using that corresponding angles theorem. So let's look here at the next one here. Kind of similar, just maybe it's a different one here. So really just need to practice identifying the different angle pairs, and then usually you guys are pretty good after that. So this one's dealing with angle 2 and 7, so I'm kind of looking up there at that. We're given that the lines are parallel. Since they're touching parallel lines, we know 2 is congruent to 7 because of the alternate interior angles theorem. So we'll write, if lines are parallel, then we'll say alternate interior, and I'm going to abbreviate both of those. Alternate interior angles are congruent. That's really all you write there for those. And then every now and then you're going to get a couple of them where you actually got to write a little bit more here. So this is using the same figure. A is parallel to B. So then we're going to say 6 and 7. Those angles there will be supplementary. All right, so that looks like your same side interior theorem there. So we'll write it out. And this one's a little bit different here. If lines parallel, then same side interior, or you could say consecutive interior. Usually I teach it as consecutive interior, but same side interior, consecutive interior angles are supplementary instead. And then I guess this next step here, they're just saying, okay, well then that means they add up to 180. And then we, learned that in the last unit that's just called definition. Whoa, there we go. That's called definition of supplementary. what it means to be supplementary. The angles add up to 180. Supplement. There you go. All right, now we're going to switch gears here. We're going to start out with the given angles are going to be congruent or maybe supplementary, and then therefore we can say the lines are parallel. And the way you write your if-then statement, you kind of just reverse it. It's almost like the converse, I guess, because you're using the converse versions of the theorems here. So now we're saying 6 is congruent to 8. So we're starting out with that, and since they are touching two lines that are cut by a transversal, we're going to say if corresponding angles are congruent, then the lines are parallel. And that's how you write it. So you basically swap everything around. It's the converse of what we have been doing there. So let's see, what do we have? 3 and 6. Let's find where those are. 3 and 6, there they are right there. So we're starting out saying that 3 and 6 are congruent. Those are alternate interior angles. So then we'll use the alternate interior angle converse theorem. So if alt interior angles congruent, then your lines are parallel. That's it right there. So those are pretty straightforward, you know, just one or two, some of them are two-step proofs there, but really not much going on there. Pretty straightforward. Now, we'll start kind of, you know, getting a little bit more challenging as we go here, because these right here, I guess we're going to prove eventually that 5 is congruent to 4. Now, yes, you could technically just jump to the end and say, hey, those are alternate exterior angles, but I guess what we're trying to do here is prove the alternate exterior angle theorem going on. So let's look through the proof here. Maybe we can kind of identify the different things here. They start us out. Whoops. They start us out with A is parallel to B. That's our given thing right there. So we'll write given for our first reason. Okay. Now we're going to say 5 is congruent to 7. All right, and since we know that those are corresponding angles and we have the parallel lines, we're going to say if corresponding angles are congruent, or actually, I'm sorry, I'm writing this backwards. If the line's parallel, then corresponding angles are going to be congruent. All right, so that is your corresponding angles theorem right there. Now we also know that 4 is congruent to 7, so we need to go up here and look and see why that is. Oh, and okay, so 4 and 7 right there, those are vertical angles, so we can use our vertical angle theorem. Which, remember, that just says all vertical angles are congruent. And then check this out. We got 5 is congruent to 7. 4 is congruent to 7. So therefore, 5 is congruent to 4. We call that the transitive property. When you're kind of jumping to different conclusions, or essentially just setting everything equal to one another. So we essentially just proved the alternate exterior angle theorem, kind of based off all that information. So anyways, you just got to kind of walk through and look at all the different angles, look at what they start you off with. All right, I guess this one here, we're trying to prove that the lines are parallel, so they're going to give us a pair of angles are supplementary, so let's go and identify that. So 1 and 4 apparently are going to be supplementary. We don't have a theorem for that specifically. I mean, we could probably make one up, but anyways, we'll use that here. So the first thing, usually that's given. Those were given to us that they're supplementary. Therefore, a measure of angle 1 plus measure of angle 4 is 180. That's what it means to be supplementary. So we say definition of supplementary. And then now they're switching gears. Now they're saying measure of angle 3 is now congruent. Or I'm sorry, the measure of angle 3 plus a measure of angle 4 is equal to 180. And I didn't see a step saying that 1 was congruent to 3 yet. So I need to go look up here and see why 3 plus 4 is equal to 180 right there. And actually, so since I see that right there, 3 and 4, they make a linear pair. And linear pairs are always supplementary. So I'll say something about linear pair. I think you could put like a linear pair postulate there if you want to write that, which says that all linear pairs are supplementary, which therefore they add the 180. I guess you could add in an extra step. You could say 3 and 4 are a linear pair, and then you could say then after that, therefore they add up to 180. You could add in an extra step there, but I think we'll be all right without that. Linear pair, something about that. Now the next step here, they say 1 plus 4 equals the measures of 3 plus 4. And what I'm seeing here is notice that 1 plus 4 is equal to 180, 3 plus 4 is equal to 180, so therefore they're equal to each other. And so that's actually going to be your transitive property there. Setting everything equal to one another. I guess this next step, sometimes you'll see people write this next step out here. Angle 4 is congruent to angle 4. We call that the reflexive property. And since those are equal to each other, we can essentially subtract the measure of angle 4 from both sides, which that looks like what we're going to do right there. So now if we subtract those and those cancel out right there, then all you're left with is 1 is congruent, or actually the measure of angle 1 is equal to the measure of angle 3. So you're essentially subtracting the measure of angle 4 from both sides. So we call that subtraction. Subtract. And then property of equality right there. And then at the very end you got A is then parallel to B. So let's verify why real quick. So let's go look at angles 1 and 3. And angles 1 and 3, there they are right there. So those are corresponding angles. We proved that 1 and 3 are congruent and they happen to be corresponding angles. So therefore, since they're congruent corresponding angles, we can therefore say that the lines are going to be parallel there. So that's the converse of the corresponding angles theorem. So we'll write, if corresponding angles are congruent, then the lines A and B, so you can just say then lines are parallel. And then there you go, there's your proof right there. So you'll get a lot of practice of that in the homework. There's a couple of them in there that'll be like that. We're going to switch gears now and talk about perpendicular lines and what that means, and the different theorems that we can talk about with these here, and then we'll kind of just look through some of the examples. I think we do a little bit of distance here in a minute. So let's take a look here. You got the perpendicular transversal theorem. If a transversal is perpendicular to one of two parallel lines, then it is blank to the other. So check this out. Since we have corresponding angles theorem right there, and those are parallel lines, we can say J is also going to be perpendicular to K. All right, and that's kind of just extending, you can say either your corresponding angles theorem, you can actually use any of the main theorems that we kind of talked about in the last two lessons there, but they'll be perpendicular to the same line there. So if one's perpendicular, the other one's got to be perpendicular if the lines are parallel. All right, same thing, kind of different here. If in a plane, and here's the key thing, it's got to be in a plane. So if in a plane, in a single plane, if two lines are perpendicular to the same line, then they are blank to each other. So here you have these two lines. The P is perpendicular to M, and then P is also perpendicular to N. So therefore, M and N are going to be parallel to each other. And the key thing is they talk about it being in a plane. You could do an example of this where you have two lines that are perpendicular to a single line, but then they wind up being skew instead of perpendicular. And it's kind of hard to draw on the iPad, so your teacher could probably show you an example of that. But it's really hard to draw actually on the iPad here, so I'll go ahead and skip talking about that any further. But okay, determine which lines, if any, are parallel based off of what we see in the diagram. Now, eventually, you could probably go prove that all of the lines are parallel and then perpendicular and so on. But based off of what we see in the picture initially. I think that's what they're kind of going for here. So anyways, I'm looking here. I see that x is parallel, or I'm sorry, x is perpendicular to R and S, so therefore R and S need to be parallel. And then you could say what y is that they're both both perpendicular to, what line is that, to x, I guess, line x. Okay, let's see what else we got here. I guess I'm seeing here as well, you have this angle, right, this line right here, x is going to be perpendicular, or I'm sorry, parallel to y, because they are both perpendicular to R right there. So let's write that x and y. So they are both perpendicular to R, I guess. Okay, now the next one here that I see going on here is I see line S, that's perpendicular to X and Z at the same time. So we can say X and Z. And those are both perpendicular to line S. Now the last combination that looks like you could do, but based off the picture you can't necessarily say, I think right away here, is Y and Z. So if you look at Y and Z, they're not both perpendicular to the same exact line. Now you probably could go through and eventually prove that these lines would be indeed parallel, but based off of what we see right now and what's marked, we don't necessarily know for sure that Y is perpendicular, or I'm sorry, Y is parallel to Z. So you got to be kind of careful on that. It's just based off of what we see initially in the picture. So if you want to write yourself a note, you could write, Y and Z. You could prove that they're parallel, but based off the picture right now, you can't. Let's see what we got here. If C is perpendicular to D, what do you know about the sum of the measures of angle 3 and 4? Well, since they're perpendicular right here, and 3 and 4 need to add up to 180 because they're a linear pair, we can just say the measure of angle 3 is equal to 90, and the measure of angle 4 is also equal to 90. And that's because I guess they're a linear pair. They got to add up to 180, and then all right, C is perpendicular to D, therefore that makes a bunch of right angles. And then after you say that they're right angles, well, all right angles are going to be congruent, so they're both going to be 90 degrees. That's kind of how I would explain that. Let's see here, is C parallel to D based off of the picture? So we'll go based off of the picture once again. You could probably go and prove, both of those eventually, but let's see here. So you got C right there, you got D, and they are perpendicular to this common line here, A. So I would say yes. Yes, because they're perpendicular to line A. Okay, what about B and D? Are those going to be perpendicular? So here's line B, and then here's line D right there. And based off of what I see, I don't see initially something that marks those perpendicular. So I would say not initially. But you could go and prove it eventually, because you have perpendicular and then perpendicular, so therefore B is parallel to A. And then after you say B is parallel to A, well, then you have this line here that's got a right angle, so therefore this has to be a right angle as well. So you could eventually go around and prove it, but not initially. So maybe we can say you must prove it. So you'd have to write out like a formal proof for that right there. Okay, okay, this next thing here, the distance between 2 points is a straight line. That is because when we think about distance between two things, we're talking about the shortest distance possible. How do you ensure that the shortest distance between two parallel lines? Write a conjecture and explain your reasoning. So if you have two parallel lines, here's an example right here. there's many different ways you can think about your distance here. You could say, okay, maybe the distance from this point right here up to like maybe a point way up there, and you can keep doing that. But we always talk about the shortest possible distance. So if you go and measure all these different lines I draw right here, the shortest possible one that we can draw between those two parallel lines will be always perpendicular to those parallel lines. So we always want to think about the perpendicular distance there. So how do you ensure the shortest distance between two parallel lines? You use the distance that is perpendicular to both parallel lines. Use the distance that is perpendicular to both parallel lines. All right. This is kind of out of place here, but I guess we're going to use some perpendicular lines to go and find some of the different angles that we have kind of going on here, and then I guess we get back into the distance, kind of a funky order there, but that's okay. We're going to go find all the angles. Now, I've done a couple of these with you guys already. The way I do it, I don't look at any of this stuff first. I go and actually find the individual angles first, and then you can go find like the sum and difference of a bunch of the other angles going on here. The first thing I see here, I see a right angle. So if I see a right angle, I know that those two angles, the 3 and then the 65 degrees, that needs to add up to 90. So if I do 90 minus 65, I'm just writing this out so you kind of see where everything comes from. That's going to get you the 25 degrees there. All right. And then, so yeah, we can go put 25 degrees. And then you got a vertical angle going on here with 1 and 3. So then that should be 25 up there. Therefore, 65 should be over here by angle 6. They mark these with the little hoops there. They mark those two angles 6 and 5 congruent. So 5 has to be 65 as well. So then therefore, angle 4, if you go and subtract, you're getting 25 degrees right there. And then also remember, if you have a right angle going on, then you have another right angle all the way around your figure there. So you got 38 degrees there. So we need to go 90 and then minus the 38 there, and I think that's so is that 52 degrees. And then there you go. So you got all your angles, and then you can go fill those in to the side. So angle 1, what was that? That was 25 degrees. I guess there should be little m's out in front of all these here, but I'm going to just kind of speed it up here. Angle 3, we also said 25 degrees. 5, 65 degrees. Angle 2, 52 degrees. Angle 4, 25 degrees. Then angle 6, 65 degrees. So I guess, use the idea of that you have right angles there, but we've already kind of seen that problem, so it's really not too bad there. All right, so look at this. You got a partial map of a town is drawn on a diagram where units are measured in feet. So I guess like each of these is like 100 feet, it looks like. Okay, line HL represents Main Street, and then CM represents 4th Avenue, and then point L represents the library, point C represents the center of town, and point H represents the high school, and point M represents the medical center. Find the distance between the medical center and the high school. Okay, so that would be this line right here. Now I'm going to do a lot of erasing and stuff, so just bear with me on that. Now this right here, you're just doing a one-dimension distance right there. So distance, you just need to take the absolute value of the difference of those two numbers there. So that part A, not too bad here. We're going to just go 900 minus 200. Almost counted that wrong there. So I get you 700, and then I guess they said this was in feet. So we'll say 700 feet for that distance. Let's see what we got for step B here. How far away is the medical center from the center of town along 4th Avenue? Now remember, 4th Avenue right there, that's I guess the line CM, and then we're going from the center of town to the medical center there. So we're just doing straight up distance right there. And kind of a couple different ways you can do this. I usually think about distance in terms of Pythagorean theorem, but you could also use a distance formula here and write these as ordered pairs. Like this first one's like 900, 300. And then this next one up here is 500, comma, what do we at? 500. Oh, there it is, 600. Looking wrong right there. And what I would actually do here, it may make it easier just if you consider these like, 1, 2, 3, 4. Whoops, I can't mark them there. But yeah, 1, 2, 3, 4, and then just go add on 2 extra zeros at the end. Might be a little bit easier if you do that. So anyways, I'm going to go in terms of Pythagorean theorem here. Now, let's see here. This horizontal distance there, that's got to be 4 there. Or actually 4 units, technically 400. And then also you got this 300 going up and down. So you could go and do Pythagorean theorem. You could say 300 squared plus 400 squared, and then equals your c squared. Now remember, this will be very similar to 3 squared and then plus 4 squared, which I'm going to do there, and then equals to c squared. And then I'm just going to add on the 2 extra zeros at the end, just because it makes the numbers a little bit smaller. So it's 9 plus 16 equals c squared. It's 25 equals c squared. So then c is equal to not just 5, you got to add on your 2 extra zeros. So we're going to say 500 feet there. And that just makes the numbers smaller where you can actually do it in your head versus using a calculator. Okay, what is the distance if you walk from the medical center to the library along 4th Avenue and Main Street? So let's see here. Main Street, that is HL. So I guess what we're going to do here is we're not going to walk the direct path. We're going to walk from M to C, and then you're going to go C to L. Okay, so that right there, essentially you're just doing 2 distances there. So then we'll go and do, I guess, Pythagorean theorem again. So we already know that this is 500 feet going diagonally, and then I guess we just need to find this dimension here. So it looks like you're going up 200, and then it's 200. So just like I did for part B, you can say it's 200 squared plus 200 squared equals c squared. But I'm actually just going to do 2 squared plus 2 squared equals c squared. And then I'll just add on the 2 extra zeros. And that's 4 plus 4, that'll be 8. And then if you do the radical of both of those, and then break down your radical, 4, 2, 2, 2, that'll be 2 square root of 2 for the distance. Now usually in word problems, we don't use radicals for the distance. So I'm going to go ahead and just punch out whatever, the square root of, or 2 squared root of 2 is. And it's about, I'm going to go out a couple decimal places, 2.8 to, let's go 8.4. And remember, we had to add on the 2 extra zeros, so I'm going to bump that decimal over 2 places. So about 282 feet, and then I guess you got the 0.84 right there. So that's that distance right there. That's the second part of the distance. And remember, I have to go back now and to go 500 plus a 282.84. The reason we're doing that is because we got the 500 first, and then you got that 282 distance right there. So that'll be 782.84. All right, and then I guess we got this next one is 4th Avenue perpendicular to Main Street. So I guess we just, to go and test if something is perpendicular here, it's actually, we kind of get into this into the next unit. We want to check the slopes. So like an example of like a slope here, you could have like 2/3 a perpendicular slope. The trick for that, you guys learned this, you learned this in Algebra 1. You need to flip your fraction, so 3/2, but then it needs to be going in the opposite direction, so it needs to be going down. So they need to be opposite reciprocals for the slope. So I guess I'll go back here. I'm going to kind of erase this here because I got a bunch of junk I don't need here. And I'm just going to go find the slope here. Now, it's up 200 and then over 200, so it's kind of like having a slope of 1. So that's a slope of 1 right there once you reduce it. This other one right here, checking the slope, it's down. So notice it's down 300 and then over 400. Rise over run, remember that. And then, well, then that just reduces down to 3 over 4. Now, those are not opposite reciprocals there, so are those streets perpendicular? The answer is no. And that's because of the slopes right there, if you want to draw an arrow to that. And that is it. So actually, I guess we didn't have any in the notes where we did the perpendicular distance between the parallel lines, but you'll probably see that in the homework, so just look out for that. You would just need to find the distance. Oh, you know what, actually, too? Now I just realized I didn't do this problem, so I'm going to come back to here real quick and do that. I apologize. Thought that was weird that we didn't do an example like that. So finding that perpendicular distance, it's just you can use your distance formula. Those last few examples I did Pythagorean theorem. I'll do the distance in this case. So 2 comma 3, 1 comma 2. Remember with distance formula, it doesn't matter the order that you do your x stuff with. So I'm going to go 1 minus negative 2 and then squared, and then do your y's. The difference of your y's, 2 minus 3. Alright, so that'll be 3 squared, and then that'll be negative 1 squared. Alright, which is going to be 9, and then plus 1. So that'd be square root of 10 would be your distance. So I apologize about that. But anyways, that is it there for your lesson today.